My name is Chen, and today I'm very glad to talk about our work about binary search in the context of the secure computation. And this work is a joint work with my advisor, Professor Marina Blanton from University of Buffalo. So first is the outline of this talk. So we will briefly review the background, also the existing solutions for this problem. After that, we will go through two or three of our proposed solutions. First is about the background. So as we know that the secure computation is a technique that could somehow enable multiple parties to jointly evaluate a function or algorithm without revealing any information about each party's private input. So by using this technique, we can somehow make sure that the data owner no longer need to worry about the sensitive information in their private data will be leaked. So that we believe that this technique will be helpful to eliminate the barrier of sharing sensitive data. But the problem of this technique is that it's not quite easy to design an application in the context of the secure computation, especially if we want to do something like data access or data retrieval. So we will see an example about why it's non-trivial. So we will use an example about binary search. And for sure, binary search is something that almost everyone on Earth can do. But the problem is that it's not quite easy to do it in the context of a secure computation. Like this binary search, what we do is just, for normal binary search, what we want to do is just like we can do log times of memory access and comparisons until we reach the target element. But what if the data here are private? For example, the input array are private, and also the target key value are also private. So the first idea is that like, okay, we can protect this information or somehow encrypt these things. But actually, this is not good enough. This is because that we can still, the access pattern here is still available to everyone. For example, here we can see that the second access is trying to touch one element in the right half of the array. It means that someone can tell that we are trying to access an element which is somehow bigger or larger than the medium of the entire array. So actually, the idea here is just like, we not only need to protect the data, we also need to protect the data access pattern. So in other words, we want to achieve a property which is called obliviousness, which means that we want to make sure the behavior of our program or the behavior of our algorithm should be data independent. In other words, so no matter what kinds of data we input to the algorithm, the access pattern or the behavior of the program should be independent of the input data. So we will try to address this issue in this question. In this work, we proposed several protocols with different properties to conduct a binary search in the context of a secure computation. And eventually, one of our protocols could achieve a sublinear communication complexity. And also, our work could also support write operation. But today, we will only cover the search protocols. So a little bit more details about the definition of the problem. So we will assume that we are given a private array, which is sorted, and each element in this private array are secretly shared among multiple parties, which means that for a single party, they will not be able to access the value of each element. And also the private, the key value here will also be private. The target key value here. And what we want to do is that we want to retrieve the element that has the key value, which has the smallest k that is equal or bigger than the target key value. But this is just the setting we use as an example. It's pretty easy to switch other settings. For example, to other settings. For example, if we want to retrieve one element that has that has the largest k, which is equal or smaller than a target k element, we can also do that. But we just use this setting as an example. So as we discussed previously, the key point here is how can we achieve the obliviousness, or how can we hide the access pattern. So when we are talking about hiding the access pattern, the first idea in our mind is to use ORAM. So for sure, ORAM is something just designed for this purpose. It's called hide the access pattern or hide the memory access pattern. But the problem of ORAM is that it's, for each ORAM access, it's somehow costly, especially if we want to apply it in a small to medium data set. So another solution is we can just do a linear scan or linear search. So this is also the starting point of this work. So the idea of the linear scan is that instead, we are looking for one element. We just touch each element. We just do comparisons between each array element with our target value. After doing such a bunch of comparisons and also some other operations, we will be able to generate a tag array where only one element is 1 and all the other things are 0. So this one will represent the element that we want to retrieve, so that we can just do a dot product between the original array and the tag array to take out the one we are trying to access. And for sure, the linear scan solution is pretty easy to implement. But the problem is that, the drawback of this solution is that we need to do linear times of comparison, which is, for the comparison operation, it's pretty costly. It's also very costly in the context of the secure computation. So our first solution is that we propose one theoretical solution, which is try to reduce the number of comparisons from linear to log times, which is to make the solution more like a binary search. So to do so, we proposed a hierarchical structure. Actually, for this structure, it's somehow pretty close to a binary search tree. So there will be in total of log m layers here. And when we are trying to do a binary search, we just start from the very top layer. During the first search, we touch the first layer. For the next search, we touch the next layer. This means that the order of accessing these layers are fixed and also public. We don't need to hide this information. The only information we need to hide is which element we access in each layer. So based on this structure, actually, there's lots of interesting things that we can do, and we propose two solutions. One is tag-based, another is rotation-based. The difference between these two solutions is just about how we process the access pattern for each layer. So we would only cover the tag-based solution here because it has a somehow better complexity. So for our tag-based solution, what we do is that we just start from the top layer, and we touch one element in the top layer and do a comparison, and based on the comparison results, we generate tags for the next layer. For example, here, the tag for the second layer will be 0 and 1. It means that the second element will be accessed or taken out. So the 17 will be taken out. And we do another round of comparison and another round of tag generation for the next layer until we reach the very bottom layer. So in the tag-based search, we can see that we reduce the number of comparisons from linear to sublinear, for log times, because we only need to do one comparison for each layer, and there are in total of log m layers. So because of this optimization, we can see that the communication cost has been reduced a lot. But the drawback of this, the tag-based solution is that the run complexity is somehow higher because we need to process each layer one by one, and each layer will cost us 5 rounds. So in total, there will be 5 times log m rounds. So one observation is that can we somehow combine these two things, because the linear scan has a constant run complexity, and the tag-based search has a somehow better communication cost. So what do we do here? Here is that we proposed our first hybrid solution, which is trying to reduce the number of rounds by combining these two things. So what we do is that, so in our tag-based search, what we do is we touch each element and, we process each layer one by one, and each layer will cost us 5 rounds. So actually, although there's only 1 or 2 or 4 elements in the top 0 layers, we still need to cost 5 rounds for each of them, which means that, wow, somehow wasting some time for the top layer, for layers that has fewer number of elements. So what do we do is just like we combine all these top layers. The layers has fewer number of elements. We combine these things into a single array, and then use our linear scan solution to process this combined array. Then at some point, when the layer size is somehow bigger, we switch back to our tag-based solution. So by doing this, we can somehow reduce the run complexity by a constant number. And this number will depend on how many layers we process using the linear scan solution, and at which point we switch back to the tag-based solution. So after the optimization about run complexity, so let's look at the complexity of the communication cost. We can see that although we reduced the number of comparisons in our tag-based solution, but actually the communication cost is still linear. It linearly depends on the input size, because you can see that there's a m in all these for all these solutions. So in our very last solution, which is our second hybrid solution, we will try to optimize the communication complexity from linear to sublinear. So to do so, before we do a search, so what we do first is that we split the entire array into multiple chunks or into multiple subtrees, and we take out the largest k in each subtree and use that k to represent each subtree. And after that, we will be able to get a somehow shorter array. So, and then we can just do a binary search or do any, just do a search by using any of our previous search protocol on this shorter array, and to generate a tag array where only one element is 1 and all the other things are 0. And this one here will represent the subtree that contains the target element. And so after we get this tag array, we can do a dot product between the original array and our tag array to take out the target subtree. And then we do another round of search on the subtree to get out the target element. So the total cost will be 2 rounds of search plus 1 round of dot product. So for more details about the cost, so we can just assume that each subtree will contain alpha element, and in total we will have beta subtrees. So for sure, alpha times the beta will be equal to m. So for the cost of our first search, because our first search is conducted on top of an array of size beta, because there are in total of beta subtrees. So the cost for the first search will be big O of beta. And for the dot product, because the complexity of the dot product depends on its output. So, in this case, the output of this dot product is a subtree of size alpha. So the complexity will be big O of alpha. And for our second round of search, because this search is conducted on top of an array or subtree of size alpha, so we'll have another big O of alpha. And because we know that alpha times the beta is equal to m, so it's easy to calculate that. If we use the setting alpha equal to beta equal to square root of m, we will be able to achieve a sublinear complexity. Yeah, because of this optimized communication cost, you can see that our last hybrid solution will outperform all the other solutions, including the ORAM work. But at some point, when the array size is pretty large, the ORAM work will eventually outperform ours, because the ORAM work still have a better computation complexity. Yeah, so a quick takeaway is that we proposed several protocols to conduct the binary search in the context of the secure multiparty computation. And one of our protocols could eventually achieve a sublinear complexity. Thank you.